The title of this seminar is Holdover and Long-Term Extrapolation. This is the last of my 4 seminars. So, first of all, as an introduction, I will remind what was the problem at this time. This time it was 25 years ago, at the end of the past century. The job from people of orbitography of CNES, the French Space Agency, was to qualify the oscillator which should be in the Galileo satellites. And in order to do that, the needs for orbitography was to know perfectly the behavior of the clocks, because it was known that the satellite should be visible during some times, but there was also sometimes where the satellite could be out of visibility during, let's say, a few hours. So it was necessary to predict the behavior of the clocks, and the requirement of the orbitography were expressed in terms of the time during which we can consider that the extrapolation of the behavior of the clock is compatible with the needs, which were of the order of a few nanoseconds for 1 hour, let's say. But the problem is the fact that this type of requirement doesn't meet the general specification of the oscillator makers, because oscillator makers generally say that my oscillator has for instance, an Allen deviation at 1 hour, which is 10 to the minus 13, or they say that they have phase noise, which is of a few dB and so on, but it's not directly connected to what is the requirement of the people of orbitography. So CNES asked me, I think it was in 1999, to make a bridge between these 2 communities in order to translate the needs of orbitography in terms of which are understandable by the manufacturer of clocks, of oscillators, of ultra-stable oscillators. In other words, we consider that the red curve, which is here, concerns the behavior of a clock, for instance, an ultra-stable oscillator. So we are able to observe it during this interpolation time, which is here, TM stands for measured time. And after that, let's imagine that the satellite is no longer visible, so we can continue by using the fit which has been performed over this time. And of course, there will be a discrepancy between the fit which has been done and the real behavior of the oscillator. And during the extrapolation time TP, the difference between the fit and the data is called the time interval error, which is here for this. But you see that it will increase, obviously, if it will increase with time. So, of course, it's one of the possibilities of the noise, but you know that this discrepancy is due to the fact that because there is noise, there is not only a drift, but there is also noise, and the noise will introduce an uncertainty on the quadratic behavior, on the coefficient of the parabola. And this error on the coefficient of the parabola will make this discrepancy increasing a long time. So if we look just on the residuals of this data, which are here, you have something which Tm is the measurement time and Tp is the prediction time. Okay, so I remove, I look at the residuals. So if you look at the residuals, you remove the parabola from the data, the fit from the data, and you have something which is very small in the interpolation period, which is here during Tm, but which will diverge during the extrapolation period, during Tp. And these are different realizations of the same type of noise. And you see that if you look at what happened exactly now, you can make an histogram, and I did it with, I think it was 10,000 realization, something like that. And you see that it's perfectly Gaussian. It's not surprising. We have a Gaussian behavior, and what is very important is to be able to measure what is the standard deviation of this random variable, which is centered because it's centered to 0, but it could be more or less, you see a few, in this case, a few hundred of nanoseconds. Okay, so the method was to find to predict what will be this discrepancy. So we have to deal with different type of noises because the clock could be affected by different type of noises. It could be white noise clocks, so it's generally the easiest part because it's a Gaussian noise. There is no correlation between samples and so on, so it's very easy generally to deal with this sort of noises. But we can also have 1 over f, which is much more difficult. And worst, we should have also random walk, which can, which no longer have, which doesn't, of which the variance doesn't converge because it depends on the length of the sequence. So it's generally something which introduces more errors. So we have to take into account the fact that oscillators can be affected by this type of noise. What is important also is to remind that here I express the noise in terms of frequency deviation spectral density, but it can be also expressed in terms of spectral density of phase, of more or less, not phase exactly, but of time error, of phase time. And in this case, you have k minus 2, k minus 3, k minus 4. So we remember that this coefficient are linked to the previous one by a factor 4 pi square. But I will deal with this result, this coefficient, but it can be changed very easily. So first thing that I do, it was to look concerning two types of drift, a linear drift or a quadratic drift, and 3 types of noises, the 3 ones that I show you. So I made simulation and I observed what was the discrepancy during the time. In fact, you are here a time which is the ratio of the extrapolated time over the measured time. Here it's 1, it means that you have, let's say, observe the oscillator during 1 hour and you look at what happened 1 hour later. If it's 10, of course, it's 10 times this time. And so you see that it increases. It's not surprising. Of course, also, if you have a linear fit, you see that the linear fit increase not so quickly than the quadratic fit. The error for the linear fit increase not so quickly. And you see also, and it's not at all surprising at all, also, that the redder the noise, the faster the time interval error increases. And for white noise, we have something which is like that, but for random noise, we have time interval error, which is almost 3 times the previous one. So we have to deal with all of this type of noises and all these possibilities, quadratic or linear fit. So we need to make an interpolation, and so we should choose the best interpolation function, which will allow us to make this fit. So remember that we have a sequence of n time error data x of t with a sampling period tau 0, and each tk which is here have an increasing step, a sampling step of tau 0, so you have tk equal k for t0, and you have to do a classical quadratic least square interpolation, first option. You have x of t, which could be considered that the sum of a constant plus a coefficient which is linear multiplied by 10, the quadratic coefficient multiplied by the square of the time plus noise. But there is also another possibility, which is to use the so-called Chebyshev polynomials. And in this case, we have here a polynomial which is of degree 0, which is constant, degree 1 for phi1, degree 2 for phi 2. And the advantage of doing that is the fact that you have P0, P1, and P2, which carry the dimension of x, which are in seconds, whereas we have polynomials which are dimensionless. It's completely opposite to this one, where C0 is time, C1 is dimensionless, and C2 is 1/second square. So yes, this is what I told you. So the first three Chebyshev polynomials are dimensionless, but you can invent, of course, other Chebyshev polynomials. But since we are interested in a quadratic fit, we only need the first three. So what are the Chebyshev polynomials? You have just a look here with an example with 100 samples. So imagine that you have 100 measurements. You see that they are perfectly symmetrical from 0 and from the half of the sequence. The first Chebyshev polynomial phi 0, which is here, is of course something which is constant. The advantage of this one is the fact that it's normalized. What does it mean? It means that if you make the sum of all the value for the 100 measurements we have here, 100 step we have here, you have exactly 1. So it means that the value here is 1 over square root of n. N is equal to 100, the square root of n is 10, 1 over 10 is 0.1. That's it. If we look at the second one, which is here, phi 1, you have something which is increasing, which crosses 0 exactly at the middle of the sequence, and which continue by increasing, of course, linearly. And the advantage is the product of these two polynomials, the sum of the product of all the elements, is equal to 0. So it means that they are orthogonal. And of course, it's also another property of the Chebyshev polynomial. The sum of the square of all the green dots which compose this straight line is equal to 1. It means that this is the property of the Chebyshev polynomial. It's at the same time orthogonal and normalized. And it's the same for the last one, which is a parabolic one. You see that it's perfectly symmetrical. And there is also a third polynomial, which is orthogonal to the previous two ones, and which is also normalized. So this is really the advantage of the Chebyshev polynomial. So I already told you that. So for each polynomial, the sum of the square of each quantity is equal to 1. And if you have two different polynomials, the product here is equal to 0. So it means that, and it's very important for this reason, it means that the Chebyshev polynomials are orthonormal, and it means that they are uncorrelated. And this is a very important feature, a very important property, because it means that it will not be possible to confuse this different polynomial, and it means that if you make a covariance between this polynomial, it will be equal to 0. So we can express that in a matricial form. So you can consider that one of the polynomials is equal to a vector. Each component of the vector are all the time steps that you can use, and you can compose a matrix phi of you put the 3 columns corresponding to the 3 vectors of the 3 polynomials, and you have here a matrix, and you can see that if you make the product of the transpose matrix by the matrix itself, you have identity matrix. So it's another way to consider this property. So how is it possible to estimate the parameters P0, P1, P2? So remember that we have a sequence of time error, x. We have 2 or 3 parameters if you want linear or quadratic estimation. We will focus on quadratic estimation. And you have the noise, which is a vector which has the same number of components as the noise. We have a value of noise for each time sample. And you have to estimate the parameter. So remember that the quadratic model, the linear quadratic model, is expressed as this in this form. So you have x, which is the vector of the time error samples, which is equal to phi multiplied by the parameter plus the noise. But you can see that if I multiply each part of the equation by the transpose matrix, the transpose of the matrix phi, you will have here an identity matrix, so you have directly P. So it means that it's very easy because you can consider that the mathematical expectation of E is equal to 0. So you retrieve only that, and you see that in this case, you can retrieve P by multiplying X by the transpose of the matrix. So it can be obtained directly by multiplying each value of the polynomial multiplied by each time error. So it's very easy. It's much easier than to perform least square interpolation. You just have to do a summation, and you have already your parameter. You have the estimate of your parameter. I forgot there is a hat here. It means that it's the estimate. Of course, the true parameter P0 and P1 and P2 are not accessible. You just are able to have an estimate, and this is the reason why there is a discrepancy between the data and the fit. Okay. So, what are the benefits of the Chebyshev polynomials? In my opinion, I recommend highly to use this sort of polynomials to make a fit. It's much better than the classical least squares for several reasons. Not only in this example, but generally, if you have a fit to do, I recommend that you use the Chebyshev polynomial. You will see it's very easy. First, it introduces a computational simplification, but as I told you, it's much easier to compute directly the parameters. Second, there is a total decorrelation of the estimators of the drift, of the quadratic drift, and so on, of the parameters. It's optimized against the truncation errors, because you know that sometimes if you have the fact that you have something which is completely symmetrical, you go back to my figure, completely symmetrical will minimize the truncation errors. This is a great advantage also, because sometimes the truncature errors are not at all negligible. And moreover, it's easy to convert into the classical coefficient. There are some, you can compute, it seems to be a little bit difficult, but for a computer it's very easy. So you can go from the P0, P1, P2 to the C0, C1, C2 of the classical equation, which is here. So if you want to retrieve this coefficient, it's very, very easy also. So I recommend to use that. And in this case, in this example, it was absolutely necessary because we have to deal with the correlation. If there are correlation between the different coefficients of the parabola, it should be a mess. So what are the residuals? The residuals, by definition, is the difference between the data and the fit. So this is the residuals of that we are trying to, which we are trying to work. So we have to estimate what is the variance or the standard deviation of the residuals. So it's easy to do because you just have to do that. Replace here R by x minus 5 multiplied by p, and you have this the variance of x minus the variance of all the parameters divided by n. And it's you have to. We will go back later. Remember, I already told you that this notation stands for mathematical expectation. Another point which will be important is to estimate the correlation between the samples, between a sample which is a date ti and a sample which is the date tj, for instance. You know that the autocorrelation function is the Fourier transform of spectral density, and it turns out to be only the real part which is important, and you have this relationship which is here, so it's very easy to compute. Not so easy, but it could be computed. You just have to replace here by the corresponding spectral density. You have here the low cutoff frequency, here a high cutoff frequency. Why? Because for the high cutoff frequency, it's obvious that it's not possible to have an idea of what happened during a time which, with a frequency which is higher than the sampling frequency. And why is there a low cutoff frequency? Because you have only information about the frequency, the Tm of Tp plus Tm time, which is the observation time. And so the low cutoff frequency is the inverse of this time, the Windows time. Okay. So, how is it possible to compute, to calculate the variance of the time interval error? The variance of the time interval error, you know that the time interval error is equal to x of t minus the fits, p0, f0 minus p1, f1, p2, f2, and so on. But the estimate of the fit with the estimated parameter, in this case, it means that you have to make the square of that and to develop the square of that. So you have first the squared value, which are here you retrieve what I call the variance of the data. Here you have the variance of the parameter P0. Since the Chebyshev polynomials are functions, there is no uncertainty, there are values, so you don't have to make the mathematical expectation, but you have the mathematical expectation of the parameters to the square. And after that, you have all the cross correlation between the value and the parameter, and between the parameters itself. But so as I told you, we already have calculated this one, which is Rx of t. The three parameter variances, it's possible to calculate, it's quite easy. The only parameter covariance which is not equal to 0 is this one. Remember that there is no contradiction with what I said. I said that all the polynomials, all the Chebyshev polynomials are orthogonal, but they are orthogonal in the window of estimation during Tm. Yes, if you extend the parabola outside of this window, they no longer are orthogonal. But it turns out that only P0, so the lower the lower parabola, the lower parameters, the parameter for the polynomials of degree 0 and P2 have a covariance which is not equal to 0. So we have to calculate it. And finally, we have to calculate the three mixed covariance between x of t and the parabola. And this was the job that I have to do. Unfortunately, 25 years ago, Mathematica already existed. So it was a job that I did that I performed with Mathematica. I think that without Mathematica, knowing my competence in the calculation, it would not be possible to do that for me, because generally from one line to another one, I change one sign, I change one symbol, so it would be a mess. So thanks to Mathematica, it was possible to go further. And what is the result of this calculation? It's given by this result, which are here. It seemed to be simple, but I think it lasts about 1 year between the beginning of the work and the end. Anyway, so the mathematical expectation of the square of the time interval error, let's say its variance, is given by this relationship, in which you see that there is here the coefficient of the noise. Here, this is the example of the white noise. White noise is given by this noise level, and you have something which is a power of 4 of the time, of the ratio of the time, of the predicted time over the measurement time. In all this formula, I put that it's an approximation, because the approximation is done for a number of of data which is larger than 1, but generally it's the case, because imagine that if you are looking at a clock during, for CNES it was more than 1 hour before before the satellite is hidden, it means that you have generally at least 5,000 data for the interpolation, and after that you can do the extrapolation. So n is always very large regarding 1. Okay, so you have this type of formula for this one. You have the same one for the Flickr FM. Flickr FM is much more difficult to retrieve, because Flickr is not a derivation or an integration of the white noise. It's something which is more difficult. It's a partial derivation, but it has been possible. But you see that the result is more complex. And the last one for the random walk. I focus only with these 3 noises. I didn't look at white phase noise or flicker phase noise, because generally for long term they don't have an influence which is interesting. The main problem occur with this long-term names, the frequency modulation noises. So you have here a formulation which is relatively simple compared to the one of the Flickr FM. Okay, so this was the result, and from this result you know that if you know the noise coefficient, and it's possible to know the noise coefficient by using an Allen variance, for instance, you are able to have an idea of the evolution of the time interval error. During this time, it was clear that it could be simplified in order to retrieve the square root of the variance of the time interval error by using not the noise coefficient, but by using directly the variance of the residuals, because the variance of the residuals is something which is very easy to obtain. You just have to compute it. And from this, I mean the residuals during the measured time. Of course, not the residual in the extrapolated time. So if you have, you should have the variance of the residual during the interpolated time. You can directly replace what was written here. You see that we will have the same behavior concerning what is between these parentheses, but you replace this value by knowing that the variance of the residuals are given here, and you have something which is quite simple here. You have 2 times the variance of the residual multiplied by this coefficient, and it's the same for the other type of noise. So this proves that it's very easy to do. Okay, and there is another simplification which can be done in the case where you can consider that the extrapolated time is much larger than the measured time. So I mean you observe the oscillator during a relatively short time, and you want to see what will happen very long time after. So in this case, it's very simple. You just have to remove all the terms which are not the dominant term. Here you have a t to the 4, so you can remove all them, and you will have directly this value which is here, and it gives you this one for the flicker and this was for the random walk. So it's a simplification which can be done in some times where the extrapolated time is very long regarding the measured time. Okay. So now remember, what are the theoretical standard deviation of the TIE which come from this equation, and you have these curves, and I will superimpose this curve with the data I got by my simulation, and you see that you have something which is in a perfect agreement. So you retrieve exactly what was observed. I told you that in the first. I would like to be sure that it's not cheating. Yes, this data are the same as this one, so it works. Okay, so what happens if we apply this result on a real clock? The first clock which was used was an ultra-stable oscillator, which were which were expected to place on a Galileo satellite. And you see that these limits are given by the relationship which is here. Not this one, but I think it's this one. So concerning the type of noise we have the residuals which are here, and you obtain this curve, and you see that most of the time the behavior of the oscillator remains between these two limits, which is more plus the standard deviation and minus the standard deviation, except at the beginning. And if we enlarge the beginning, you see that at the beginning it began to run out of this limit, but after that it go back in. It's not at all surprising, because when you deal with random process, if you have a standard deviation, we have generally 2/3 of the possibility to be inside and 1/3 of the possibility to be outside. So it's something which remain compatible. Another example is given here. I think it's with the same oscillator, but I'm not sure. And you see what happens. In this case, the result is a little bit different, because the standard of the deviation of the tire was fit over a 1-day sliding window. So we have clock, the behavior of the clock is given here, and you have first the limit which are given knowing the noise levels. So you see that we find something which is 5.4 nanosecond. If you compute from the variance of the residuals, of course it will change, because it will change with the sliding window, if you move the sliding window. And in this case, you have an average of the standard deviation, which is a little bit higher than the one which was retrieved from the noise level, which is 8.2 nanoseconds. And the experimental one, if you make the standard deviation of the black curve is really the behavior of the oscillator itself, you will find 7.2 nanoseconds, which is really between these two values, between these two estimations. So it seems to be very satisfactory. Of course, we are dealing with uncertainty. You don't find 3 digits of the points. We just have to have an idea of let's say a few 10% of the uncertainty. So it means that it seems to be compatible with what we found. But it would be difficult for me not to introduce a little bit of statistics in this talk. So if we want to be correct with the confidence interval, you have to mean what are really the confidence interval knowing this standard deviation. So we remember that the time interval error follows the centered Gaussian distribution. So it means that its variance is chi-square distributed with new equivalent degrees of freedom. And but number of degrees of freedom is not very simple to know, but it turns out that I make some experiment, and I obtain that the number of degrees of freedom doesn't depend on the number of the samples. It doesn't depend on the length of the measured time or the extrapolated time, but it depends only on the type of noise. If you have white FM, you have 8 degrees of freedom. If you have flicker FM, you have 3. And if you have random walk, you have 2. And of course, if you have 2 degrees of freedom, it means that you have much larger variability, and it's obvious with random walk. What happens for the confidence interval? So you know that in this case, it's a classical case with Gaussian distribution. You have to multiply the standard deviation by a coefficient which is the student coefficient. You know perhaps the student distribution which has been invented in order to do that. And so you have a small corrective in order to have really a time interval which is at 68%, the so-called 1 sigma. You have to multiply by this coefficient, which is more or less 1 if you have 1 sigma, but which is quite different if you are looking at the 2 sigma, I mean a 95% confidence interval. If you have a 95% confidence interval and you have, for instance, a dominant noise, which is a random walk, you have to multiply this uncertainty, this standard deviation by a factor of 4. So it means that you have to multiply by 4 the limits that I showed you previously on the graphs. Okay, so that's it. So now I will switch to another approach because I promised Jean-Michel to deal with the Kalman filter approach, and I will try to give you a brief overview of what could be possible to do with the Kalman filter approach to the subject of Holdover. So first, if you want to perform a Kalman filter, you have to define the model, what is the measurement, what is the state vector, and what is the error covariant matrix. So this is really the initialization of the process. So I will consider that the clock model may be defined by 3 state variables. First, there is a phase, the time error, which is something which should be parabolic. So there is a x0 plus y0 t plus d0 t squared divided by 2. You will see later on why I divide by 2, plus noise. If you deal with the frequency deviation, it's linear. If you deal with the time derivative of the frequency deviation that I called the drift, is d0, which is a constant, plus noise. At each time, all this noise are Gaussian noise. But of course, if you have a Gaussian noise, this Gaussian noise here is integrated, it will be the random walk, and here in this case, it will be f to the minus 4. Okay. The measurement, we will consider that the only measurement that we are able to do is a measurement of the time error. So you imagine that you have a time interval counter at each time t, every tau second, each time tk, I measure the value. So this is the only thing which is measured. The state vectors, of course, is composed of the time error, the frequency deviation, and the drift that I presented here in the clock model. And as I said, this one is the time derivative of this one, and this one is the time derivative of the frequency as the second derivative of the phase. And still, we have a sampling time tau, which is tk plus 1 is equal to tk plus tau. Okay. And we have to define an initial error covariant matrix. At the beginning, we don't know very well what will happen, so we can estimate that there are uncertainty on both x, y, and d, and you will estimate what are how do you know, how precisely you know the different value x, y, and d, and so it's something which is it depends on the noise that you are in the system, and the measurement noise particularly. Okay, so from here we will begin the iteration process. First, you have to make an a priori prediction. Remember that here you have the step before, so you have a value of x, a value of y, a value of d, and you want from that have an estimation without knowledge of the next step. Of course, of the next step, what you do, you have to apply this state transition matrix. I saw that phi is the same symbol that I use for the Chebyshev polynomial, but it has nothing to do. Sorry, I should have changed because I didn't remember that I have the same symbol. Don't worry about that, but be careful because they are completely different. It's not at all the same thing. Here, the transition matrix is only here to translate what was the previous state vector. So you have a vector which is here with x, y, and d. So you have, for the first line, you have x multiplied by that plus tau y and so on. So you have the behavior of what happened in x in tau seconds. So you have tau multiplied by the frequency deviation, and tau squared divided by 2 multiplied by the drift. So it's a quadratic drift is included. So you consider that you have only the deterministic part which have been determined before, which will go on. We don't consider, of course, the noise. What's something which is very important? You can also add, but I will not use it today, but you can also add here something which corresponds to the control that you can perform on the clocks, on the oscillator. For instance, you can imagine that you are able to modify the frequency of the oscillator. So it's possible, thanks to a Kalman filter, to not only fit what happens, but also modify, for instance, if you want to remove the drift. So it could be very interesting if you want to remove the drift of an oscillator, because you can adjust the frequency of the oscillator in order to minimize the drift of it. I will not deal with this, but you have to know that it's very important. It's the reason why Kalman filter was invented, because the motivation of the Kalman filter was to, by the NASA, the beginning of the Apollo mission, it was to control all what all was ongoing on in the rocket. So it was really important that to have control on all the process. But we consider here that we don't have control. We just have a fit of the data. So now we have a prediction, but we will deal now with the update, because we will use a new measurement. The new measurement, the previous measurement was in tk minus 1, I mean tk minus sampling time tau. And now you have to take this innovation, but you have to do a trade-off between the fact that if you use the prediction, you don't have anything new, but if you want to use the new data, you know that it's noisy. So you have to mix between what would be the continuity of the drift, for instance, and what will be this new data. And this is done by using, I will not detail exactly what happens here, but this is done by the Kalman gain, which is here, which is an optimization of the previous the previous covariance matrix, which is here. This covariance matrix will be modified in real time at each step in order to take into account what is the noise in the system. And once you do that, it's possible now to modify the predicted state of the clock at time 2k by using the innovation which is linked to the measurements that you perform. And doing that, after that, you have also to update the covariance matrix of the measurement and so on, as the measurement post-fit residuals. And once you get all that, you have to go to step 1 and you make a new prediction for k plus 1, for k plus 2, and so on and so on. So this is the principle of the Kalman filter. The only thing which is a little bit difficult to understand is what is going on in the computation of the Kalman gain. But it's really what is important in this algorithm. So I tried to use it very quickly yesterday, because I work on Kalman filter from Monday to yesterday. And you see that there is data which are in red here, and a first fit which was done by the Kalman filter, which is in green. So you see that in this case, it follows, it removes all the very quick variation, which are the small pikes that you see in red, but it follows quite well the data, but it's not very interesting for us, because we would like to have something which will give you what is the general behavior to fit the drift. And it's possible if you change a little bit the coefficient, and you see that here you have something which is almost a perfect drift. You have some variation because you have some motion of the data, but it could be considered that partially by drift. So is it possible to make holdover by using this type of fit? The first try that I did seems to say okay, because here I choose to stop the interpolation at 5,200 seconds. I mean, after this time, there is no longer innovation. I don't take into account the new data. We imagine that we are blind, so we are not able to see what happens with the oscillator, and we go on the Kalman filters. We see that it goes on in this direction. So it seems to be relatively correct. But if you stop at another point, here it's 4,500, you see that in this time it seems that exactly now there was a very high quadratic coefficient, and it makes that you have a discrepancy very quick in this case, and in this time I think it's not at all satisfactory. And what is the problem with the Kalman filter? It turns out that it seems to be very sensitive to the place where you stop the interpolation and when you begin the extrapolation. Perhaps it depends also on the fit, because if the fit is very tight, this dependence will be very large. But if the fit is not so tight, if you want really to have a straight line, perhaps it should be better. But there is some trap, in my opinion, with the Kalman filter. Once again, I only tried to do that 2 days ago, so I'm not sure that my conclusion is definitive, but it's something which should be we should go on with these results. So, as a conclusion, concerning the choice between Chebyshev fit or Kalman filter, I think that really, in order to have for the problem of holdover, I think since Kalman filter depends drastically on the holdover start, I think that Chebyshev is much more reproducible. So for me, it seems to be much more reliable. But you remember that some further work is needed to be very sure of this first conclusion. Second conclusion concerning the clock selection, I would say that thanks to this work, it's possible to define a criterion which is concerning knowing the interpolating period and the extrapolated time, which give you what will be the variance, the Allen variance over 1 day, for instance, or the noise coefficient, the noise levels, which would be compatible with this requirement. So it's really what was asked by Kness at this time. There is also other application. We can imagine, for instance, that you want to realize a very low-level local time scale. When I say low level, I mean that let's say a few microsecond level. What can be done is to send periodically the reference clock to an accreditation laboratory, let's say LTFB, for instance, which will exactly look at your clock, will see the drift, precise measure of the drift, and you can consider afterward that the drift will go on, and you know approximately what will be the error we will made by being confident to your clock. So you have to extrapolate the quadratic fit. Okay, but in our case, for a high-level local time scale, it would be possible also to use all the clocks available in the laboratory in the same ensemble clock by comparing them mutually and continuously. So for doing that, you need a time processor, of course. And you remove the drift of the clocks which are drifting, like the hydrogen maser and the CSO, but you can do that thanks to the cesium clock, which doesn't drift, but are not so stable. But with the Kalman filter, you can take into account the fact that you have something which doesn't drift, and you can benefit at the same time of the stability of the CSO, for instance, and of the stability, not stability, the accuracy of the clock. And in this case, you can realize in real time, and this is very important, an ensemble time scale that combines the best performance of all clocks. But in this case, I think it could be a Kalman filter with control, which could control, for instance, oscillator in order to modify in real time, for instance, quartz oscillators, their frequency and so on. And that's the end of my talk, and I only have a few references. This one is for the paper that I did in the beginning of this century, and the two theses which are here, because Antoine Baudiquet, with the part he did with BIPM works on the Kalman filter, as well as another PhD student who was his reporter in his PhD defense, which works on an autonomous and robust timescale algorithm for a swarm of nanosatellites around the moon. So the idea was to combine all the small oscillators which are in each satellite, each nanosatellite, in order to make a timescale. Thank you very much for your attention.